Let's double check, class. Welcome. Can you see the screen? Good. All right, we're beginning and finishing up topic 10, organic chemistry standard level in IBDP, with topic 10.2 finishing today. Okay, so if you remember, okay, so if you guys remember this stuff, we looked at this a little bit when we did the alkanes. Do you remember? Halogenoalkanes. We were looking at that one lesson, the making of the halogenoalkanes from the free radicals. Do you guys remember? When we broke up, you know, like a chlorine bond, and then chlorine has a free radical, chlorine dot, and then we join it onto your, you know, molecule, and you have a halogenoalkane, right? So if you forgot about that, please go back to that lesson from like last week or the week before, okay? All right, now, just to review then, we know that halogenoalkanes, we will have one of the main halogens from fluorine to iodine attached to your alkane. The general formula is this: CnH2n plus 1, X is your halogen, okay? Normally they're only liquids and they do not mix well with water, okay? So they don't really dissolve with the water very well, okay? Now, in general, these are more reactive than just alkanes, okay? So halogenoalkanes will undergo, that you will learn in this lesson, nucleophilic, okay, substitution reactions, okay? That's really what we're looking at today with these particular compounds. All right, so now, okay, so let's see. What am I looking at this picture here? We're looking at just how we made a halogen with a bromine. Oh wait, nothing big deal here. Okay. Now this one, again, you need to know that they will not mix well with water. Okay, they can't really form hydrogen bonds with the water, and so what happens is in these reactions, they're often completed in a mixture of water and an alcohol. Okay. All right. So now, dihalogenoalkane is simply two halogens substituted onto the alkane, that's all, okay? Now this one, like your alcohol that we learned last time, you can have a primary, right? And a secondary and a tertiary haloalkane. So do you remember, just like your alcohols, if I have a primary haloalkane, it's connected to a carbon that's connected to how many hydrogens? Charles, say it loud. 2, okay? And then if you have a secondary haloalkane, okay, then your halogen is connected to a carbon that's connected to how many hydrogens? Go down. 1. And then if you have tertiary haloalkane, similar to tertiary alcohol, then your functional group halogen connected to a carbon that's connected to how many hydrogens? Go down again. 0, none, okay? That's just a similar parallel to your primary, secondary, tertiary alcohols from the other day, okay? You will be asked about that on your multiple choice, by the way, just like with your primary, secondary, tertiary alcohol. Okay, all right, now, what you having, okay, before we get into understanding the reactions of your halogenoalkanes, we need to make sure and go back and understand the definition of electrophile and nucleophile. In a previous video, I said to you guys, if you saw it all, do you remember the difference between nucleophile and electrophile? What's an electrophile? What do you think it stands for if I say electrophile? Okay, so that means it is going to want to get an electron, right? That means it's electron deficient. What does the word deficient mean? Lacking, okay? Not having enough. So the opposite of that you learned in today's lesson for sure is the word nucleophile. Okay, so a nucleophile would be then, what, in your own words, one thing that wants okay, it doesn't need to get electrons. It has what then of electrons? Yeah, electron rich. It has enough, okay, to donate the electrons to something that is electron deficient. Make sense? Now, what you will be asked about too, that's also in your textbook, is a nucleophile would be something that would have an attraction to the nucleus. Okay, so that's why it's called nucleophile. You know the word phile? What does that mean? It likes, yes. It likes something. Phile is something likes whatever. Electrophile likes electrons. Nucleophile likes nucleus. Okay, so you should know those kind of like key parts of a word. So anyway, so all right. So now, in all these halogenoalkanes, you will usually end up getting like, okay, your carbon connected to your halogen, you will have polarity, okay? Because why? Electronegativity value of the halogen is always going to be a lot stronger than the carbon, right? There is going to be a delta En that is significantly larger. So there's a big difference, right? So with those halogens, okay, being the stronger electronegative element in the bond between halogen and carbon, then basically, you know, the halogen is able to draw in electrons. So if I'm looking here, the halogen is able to draw in electrons closer to itself, okay? Okay, so then that means that the carbon is able, this carbon here will be able to be easily attacked by like a negatively charged ion, which is your nucleophile. So there's a nucleophile somewhere else, then that nucleophile will be easily attracted to this quite positive, or slight polar positive charge carbon, okay? So that's really what's going on here when we're talking about the nucleophile in action. All right, so you can see here, okay, for example, like over here, so if what you have here, okay, is you have, okay, for example, this is chloromethane, right? And then, so the chloromethane, eventually, what will happen is you will have the OH, okay, so the OH ion, okay, this is a nucleophile because here, as you see, the oxygen has quite a few extra electrons on it, these lone pairs, right? So then it will react with the positive carbon. Actually, you call that also, do you guys remember the video I showed you? A carbocation? Do you remember what that meant? Carbocation from, yes, positively charged carbon, okay? So it's kind of like in a carbocation state, positively charged. Okay, so the OH would then attack that carbon, or sorry, yeah, attack the carbon and it will react with the carbon. So what we will do is the Cl will be able to pull the electrons in the bond it had with the carbon, and the electrons will just go to itself. So really what you would do is you're going to be dumping chlorine out of the original molecule here. Chlorine will come out by itself here. I didn't draw this, I forgot. There should be like lone pairs here. It's like dot dot Cl minus, okay? So you would basically have chlorine all by itself as in its own ion. And then basically much what happens is that the OH has completely substituted for the halogen. Make sense? And that's why we call it a substitution reaction. It's called nucleophilic substitution reaction because the nucleophilic involves having a nucleophile, okay, that is attacking your carbon. And that's why we get this word nucleophilic substitution reaction, right? Hopefully that's not so bad there. Okay, now another key words I want to describe for you. When I'm looking at, for example, the C and Cl bond, because this is also asked on your test, and it didn't go into much detail on your IB textbook, okay? So when that carbon is breaking the bond with the chlorine in here, okay, then what kind of, okay, did you see in my alkene video, I briefly mentioned the word heterolytic fission, this word. Everything is running out of this school. Okay. Even I have trouble spelling it. Heterolytic fission. And then we saw earlier when we did the free radicals chain reaction with the alkanes, okay, with those the making of the halogenoalkanes, we saw this other word, you remember this word? Do you guys remember it? Homolytic fission, heterolytic fission, you need to know the difference between these two. Okay, from when we did the free radical chain reaction with the making of halogenoalkanes from that alkane lesson, what was the definition of homolytic fission? Do you remember? So, okay, for example, if I have something like this, Br2, your diatomic bromine element, so it would have been like this, correct? This is your single bond between the bromine, okay? So as a homolytic fission, what is going on? Think of the free radicals that you made from that lesson. It splits, yes? So, and then it becomes something like this. Do you remember? What was my dot for? Free what? Free radical, okay, free radical. Okay, so now, why do you think I'm even using this word homolytic? The same, because it's basically splitting the electron pair equally between the two atoms. Make sense? Okay, so now when you have something like this one, carbon and chlorine, okay, and if I'm going to break that one, then the electrons will go to, so that what happen is the electrons in that bond between C and Cl will both go to the halogen, okay? So what they're saying is that in this CCl bond, both electrons from that shared pair between the two of them would just go to the halogen, going to only one atom, okay? That is what we mean by this word, okay? The heterolytic fission, and you need to know that word, okay? It's required for you to understand the two differences. That's often on the multiple choice a lot for you to separate the difference between those two keywords. So in this thing we have here in your nucleophilic substitution reaction here, in this example, the breaking of the CCl bond is broken by a heterolytic fission, okay? Before that Cl can be substituted by the OH. Makes sense? So you need to be able to describe that for just this one little reaction here, okay? All right, then, sorry, why is it not moving? Go, here we go. All right, so you please go ahead and do this right now, spend about 2 minutes doing it, part 1, part 2, okay? Try. Now, keep in mind, this is the same thing that we just saw, but look at here, I've got KOH in both 1 and 2. Why do I have KOH instead of OH? Because in the real world, in your lab, you're not gonna have some container in the stock room with just an OH chemical, you see what I mean? OH will usually come with an alkaline solution, make sense? And then we don't really care about what's happening with the potassium, okay? The OH is the one that will act as your nucleophile, make sense? Go ahead and just tell me what you think will be the, the reaction, the equation, write it out. I'll come check with you. Okay, just a second, I'm gonna show this video. I don't know if you can even see it. Maybe we can see it. No. Pardon. Stop presenting. Show the board. Try this. What? It doesn't even show. Maybe. Okay, so that's what it was earlier on the board. How heterolytic fission, the camera captures it, homolytic fission. Then the homolytic fission is like a splitting of the halogen, like that. Br dot for free radicals. And then the heterolytic fission is breaking of carbon-chlorine bond. And then all the electrons in that pair will go to just the halogen on the chlorine, okay? So that's the difference between those two words. Yeah, just a second. Here are your questions, sorry. So write that sucker out. Yeah. The OH can only come in an alkaline solution because it has to have a cation, okay? Not just in isolation by itself. And then once you do write your products, on the test, you need to identify as well whether it's primary, secondary, or tertiary. Okay, so please do that as well. Okay, when you find out what the product is, you'll be making an alcohol, right? Yeah, this is making an alcohol. So you're gonna be making alcohols in both part 1 and part 2. How much time we got left? Okay, we're good. We're good on time. Let's see. Yeah, you should be able to identify who's primary, secondary, and tertiary, even when there's still a halogenoalkane. Okay, right? So on number 1, look at where the Cl is put on that molecule, which position it's on. Oh, and name your alcohol too. Yeah, not just primary, secondary, tertiary. Name it too. Give it a name. Right, finish? Okay, here, check please. Right, so, okay, look on part 1 here. Okay, if you look at part 1, okay, so this is what it used to look like. Add it to the KOH, right? So then again, the OH will act as your nucleophile. and you're not showing much detail here, they don't expect you to show all that necessarily, okay? All they want, if they give you condensed formula like this on your IB test, then you could just show your answer as a condensed formula. Got it? So, and then here, what you do is simply replace the Cl with the OH, make sure the rest of it is exactly the same as before, okay? The OH is on the position of the first carbon, right? And then that potassium can get together with the Cl instead of leaving Cl by itself. And then you would basically have a side product here, your potassium chloride. But this is your main alcohol that you make, okay? And then this could easily be called 1-butanol or butan 1-ol. You can use either name on your test, okay? Either 1-butanol or butan 1-ol. Now, so is it then primary, secondary, or tertiary? Correct. That's right. It's primary. Okay, primary alcohol. Okay. And they will ask you to, not only is the product a primary alcohol, the original halogenoalkane was a primary halogenoalkane. Understood? So you need to be able to say either one for the reactant or the product. Okay, then on part 2, okay, so then we have this one. Okay, that just means we have 3 methyl groups here, and the carbon and then the halogen, okay? Again, using OH from potassium hydroxide. And then when you do that out, okay, like not to be lazy, but you could do it this way. Either you write it out like that, or you just keep them in your parentheses, right? So you don't have to draw them out, 3 times or whatever. And then all you do is you replace Cl with OH. Then you make, of course, KCl just like the top one. And then this is tertiary alcohol, because if you drew it out like this carbon is connected to only methyls and no hydrogen. So then it would be tertiary alcohol, okay? And then that means that the original halogenoalkane was also a tertiary halogenoalkane, right? Everyone okay so far? This is not as difficult as the alkene and some of the other ones you saw. I like this particular set of reactions. Okay, let's go back to benzene then. Okay, that lovely ring compound. Now, okay, I already gave you a little bit of a lesson on benzene before. Do you remember? We talked about in detail about the nature of the benzene compound and its resonance, right? It being electron rich of a molecule. Okay, and so we know that it's an electron rich, and then those circles or rings inside the benzene hexagon is basically trying to tell you that that's basically in this hybrid resonance between 2 structures of the benzene. Okay, but it's really a lot of delocalized, a lot of free electrons, and so basically what happens with the benzene in reactions, it likes to be attacked by an electrophile, right? So now you know what the electrophile is. So electrophile would be, those things again that are really desperate to get the electrons because they're lacking or deficient in electrons, right? So, and again, this is still a substitution reaction, but unlike what you just saw with the halogenoalkanes, we will call these electrophilic substitution reaction, okay? So you guys spell that word here. Reaction, okay? So this is basically like the opposite of nucleophilic. Nucleophilic, we just saw a nucleophile will attack the carbon. This time, okay, you have an electrophile to want to join. So in this situation, the electrophile is like, I see a benzene, okay, and there's got some extra electrons for me. So what I'm going to do is I'm basically going to somehow find a place for myself in this benzene ring and replace some hydrogen off that benzene ring. And then that way, once the electrophile is attached somewhere in the ring, then it will be able to share some of those electrons that this benzene is rich in, Okay, so that's basically what's happening here. Yeah, so I think that's pretty straightforward. Okay, and then you dump one hydrogen out. Okay, so and okay, now there's two main reactions you need to know when you're talking about electrophilic substitution reactions for benzene. What is required on your IB test, the left side at the bottom down here, is what we call the nitration of a benzene reaction. Okay, so what's happening here is that you basically going to have to place a nitro group, the NO2, somewhere in the position on the benzene ring. Orange, okay? So basically you're placing a nitro group, okay, onto the benzene ring here. Now, this reaction will take place like this. You got your benzene plus your nitric acid, and what will happen is, which you are not responsible for, so there's actually more than one step here. There's actually a series of complex steps that you are not shown in detail here, okay? But what you need to only know is that, what you are expected to know is that it's going to be a complex multiple step process, and then it has to happen under very certain conditions where you have a temperature of 50 degrees Celsius and you're using concentrated sulfuric acid for your catalyst, okay? That's all you really need to be knowing. But somewhere among those multiple steps, you form an NO2 plus ion. So this plus meaning that we're short on electrons on this NO2, okay, ion. So it will then become an electrophile because it really desperately needs some electrons, being a little too positive in charge. And then it will find a way to replace a hydrogen on the benzene ring, and then it will find its way on that benzene ring. So it will be called a nitro group, functional group, okay? And then that is basically your nitration of a benzene ring, and then you get dumped with the water here at the end, okay? So that's the first thing that you need to know for the nitration reaction. Okay, let's see what else you need to know. Okay, no. Now the next one is simply going to be, okay, replacing a hydrogen with one of your halogens. And I think you saw this already on your assignment sheet a few weeks ago. You got one where you had to name them like crazy. Okay, there's a lot of like halogens attaching to a benzene. So this is the actual reaction of how that happens. Okay, we didn't show you before. We just expect you to know the name. So basically, you would have a chlorine replace one hydrogen here. And now the specific condition you need to know is that as a catalyst, you will use aluminum chloride, AlCO3. And then that is an AlCO3 that's in a dry ether compound. That's all you need to know there for that particular condition for the catalyst. And then you will then get a chlorination. In this case, it could have been bobination, it could have been whatever, okay? This is just chlorination because it's chlorine. And then you have one chlorine on the benzene ring. And for each of these single steps, you can only substitute one hydrogen at a time, okay? So you can only really just take one hydrogen out and then take only one chlorine out. Then that hydrogen that was displaced will get together with the chlorine that's left over and make a side product, the hydrogen chloride, right? So that is, wait, come back here, we're not done yet. Where are you going now? Sit down, okay? After we're done, then you can go to the toilet. So leaving before we're done with this lesson. All right, so this is the two main things you need to know about benzene. Both of these are your electrophilic substitution reactions of the benzene, okay? You need to know that. So when you expected to know the two main ones from your IB curriculum, it's these two ones. One with nitration and one with a halo. I guess when you put a halogen on the benzene, there's a particular word for it. I'm trying to think what we call that. I think we just halogenate. Yeah, we halogenate the benzene. That's how you do it, okay? We halogenate the benzene to add a halogen onto the ring, okay? Halogenate this benzene. Okay, and now one more. Okay, benzene, like the other stuff you've seen, can also go through combustion. Okay, so basically, you just if you expected just to write it out on your paper 2, simply write the full formula of benzene, not C6H5, by the way. That's a phenyl group. Remember? That's when benzene is a functional group. But as a full benzene, it's C6H6. You should know that. Then oxygen makes CO2 and H2O. And then again, this is complete combustion. Okay? We don't making CO here. We just balance the reaction using CHO like you did with your alcohols and your alkane. Okay? So that would be something that you'd be asked to do too. Is write out the equation, balance it, and then voila, you're done with that combustion reaction for benzene. All right, now, yes? Yes. Huh? Oh, sorry. Let me go back. Which one? For adding the nitro group? No, you add okay. It's H2SO4, okay? And 50 degrees Celsius. That's the specific condition for the nitration of benzene, okay? And then AlCO3 for the other one, chlorination or halogenate benzene, okay? With any halogen. Yeah, you have to remember that. You won't have to write it out over the line necessarily. Usually that's a multiple choice thing where they ask you to, or they give you that already on your paper 2. But on paper 1, you probably have to pick A, B, C, D, which is the right condition for this reaction, okay? That's the only thing that gets people in paper 1 for the specific conditions with the arrow sign, the catalyst or temperature or whatever, okay? So, and sometimes also concentration too. They'll give you how many molars or something, okay? All right, now, okay, we did this one. Now, don't go away. That means, Kevin, don't go away. Okay, let's go to some animation to show one more time this thing. Okay, so now I want to show you, let's see. Let's go to first back to halogenalkanes. This thing, by the way, using this website costs 1,000 British pounds per year. Yes, it's very expensive and it's really not that interesting, but but it has some good stuff here, as you can see. Okay, here we go, halogenalkanes. Yeah, I included some of these little things from the, all right, let's go back again and look at the nucleophilic in more detail right here. Okay, like we saw with the first part of this slide. Okay, so again, let's look and see what happens with the reaction with the OH. Okay, here we go, the halogenalkanes. Okay, so reacting, yeah, this could have came from NaOH or KOH, like we just saw. Let's see the details. Okay, so the negatively charged hydroxide ion is attracted to the positive charge on that carbon atom. Okay, so it's gonna come break from its own alkaline, and then the electron pair on the OH donates onto the carbon atom. Okay, the increased electron density on the carbon causes the electrons in the C and bromine bond to be repelled to the bromine. This is then your heterolytic fission. Okay, and then of course you end up making your alcohol. All right, and then that leaves like this. You see how we show this? We show that halogen with the 2 electrons here, and then the charge minus. Okay. Now, another word you might be referred to is sometimes this is called hydrolysis, okay? So, but really you don't need to know that so much for IB, okay? But sometimes you see that in your textbook. All right, that is that one for this one. You can do it with other stuff too. Now, mind you that they could ask you that other stuff besides OH acting as a nucleophile, it could happen with some other ones too. For example, with CN. Okay, if you had it with a cyanide ion, okay, so it does the same thing as the OH did, okay? Again, it acts as a nucleophile, attacks that carbon, and then, of course, the Br gets broken off, right? So, and then this one is a special kind of compound called a nitrile. Okay, so you might as well be familiar with it. Nitrile is a very common thing that's used a lot, okay? Nitrile is making its CN attached to this, what used to be your halogenalkane. And then finally, your ammonia, NH3, can also act as the nucleophile. Because why? NH3, ammonia, you know this, it does have an extra pair of electrons on it, okay, the lone pair on the NH3, and then that will allow it to act as the nucleophile, okay? I hope you guys are seeing this pattern, okay, of how you do this. Now, you guys notice how the animation is being done? If on paper 2, they want you to show detailed mechanism, that is what you're expected to do. What I'm talking about is how you write it on paper 2 is showing those curved arrows, just like the animation did. You understand? Because you're showing, and then you do it like an animation. You do it step by step by step, showing the arrow at a time, who's going from where to where, who's getting attacked, and so on, okay? That is how you show real detail in the mechanisms of like a typical paper 2 answer, question. Anyways, like this, yeah, okay? That comes together. You see that? Nice, beautiful arrows. Okay. Okay. Now, let's see. I don't think you have to really do NH3, but these two are fair game. OH, definitely. Let's go back to another one. I want to show you then, after this one, carboxylic. Okay. Let's see. This one again was what you saw last time. Just to review your free radical again. You saw this already, right? Remember how we made the halogenoalkanes to begin with? Okay. Now, it's not at the end step. You were making it really from like somewhere in the middle. Okay, so when you were making it in the middle, like you were making it like somewhere in one of the intermediate steps. Okay, this is where you broke the homolytic fission. Okay, here we go, homolytic fission. And then where you start making your halogenoalkane, okay, is after you have a bombardment of free radicals. Then at this particular step, okay, this is where, okay, you create your, or starting to create your halogenoalkane right here. Once you break that off, come together, here we go. This is the start of how you make a halogenoalkane, okay? So it's coming from the free radical that you saw process chain reaction with your alkanes. That is asked really in multiple choice, okay? What are some ways that you make the halogenoalkane in the first place, right? Okay, and then, let's see. Let's go back to alcohols. Didn't show this yesterday because we ran out of time. All right, so what I'm going to show you. Substitution reactions. Why am I on here? Oh, here we go. There's so many, I can't remember which one. Here we go. Look at this. God, so slow. Paying 1,000. All right, here we go. Some more details of this one. Okay, let's look at this one. This is from yesterday's lesson. Do you remember? I didn't show you a lot of the details with, we saw it already in the PowerPoint, and then this is the animation for, how alcohol can be used to make like one of your alkenes, okay? So let's look at this. So this one is, how is ethanol made from ethene? This is an actual question you are asked sometimes. It's to show the mechanism for how, okay, the alcohol ethanol is made from your alkene called ethene, okay? So here again, there's some conditions here. You need to remember that in Celsius, by the way, sometimes. I think on the IB test, they have that in Celsius, right? So 60 to 70 ATM is the pressure, atmospheric pressure. Don't mind the megapascal. I don't know why they use that one here. You need to remember it by ATM. Phosphoric acid, there we go, as a catalyst. Okay, let's see how this works. So the phosphoric acid is a polar molecule. Okay, so the electron density in that double bond can attack the slight positive charge on one of the hydrogen atoms. Okay, so again, it's acting as an electrophile. This one here. Then a bond formed between one of those carbon atoms and the hydrogen atom. Okay, here's your carbocation form right there. Okay, water would be a nucleophile. Okay, so one of the lone pairs on the oxygen attacks the carbocation. Okay, and then the hydrogens on the oxygen is attacked with a lone pair on the oxygen in H2PO4 minus ion that broke off from the phosphoric acid. Okay? And hydrogen forms a bond with the H2PO4 minus ion. This is like a new thing, and then here's your alcohol. Okay? So this is all on video, so you can go back and look at that again, and then go back and watch the animation step by step for that one. Okay? Production of ethanol from ethene in greater detail than you saw before. Okay. The next one, other reactions. Okay. Okay, so this is from yesterday. Do you remember your primary, tertiary alcohols making aldehydes, carboxylic acids, also making ketones, and so this is that review again. We're not here. Sorry, this is the next one. Nope. Okay, where's my next one? No, I don't want combustion. God dang it, where is the next one? Where's my primary? Lost it here. Okay, never mind that one. That's the wrong one. Here, sorry. Too many, they don't organize this in one thing. Oh, here we go. Finally. Carboxylic acids with a primary alcohol. Yeah. All right, so this is your primary alcohol. Remember, you had your dichromate Cr2O7 as your catalyst, okay? And then so here, what am I supposed to do? Let me see. Oh, okay, very interesting. Right, so then they just basically added that into, or add more alcohol. Okay, and then, so here we go. Let's see what happens. Okay, so the reaction must be heated for longer when forming aldehyde. So the reaction mixture is reflux. No, that's supposed to be the last step with carboxylic acid. Oh, yeah, sorry. Yes, if you want to go to carboxylic acid, you have to heat beyond just making aldehydes. This is where you have your reflux, okay? The vertical condenser. Okay? And as the reaction boils, the aldehyde evaporates and condenses repeatedly, dripping back into the reaction mixture to continue to be oxidized. So the color changes from then orange to green when it started at brown, then orange, then green. This is supposed to be red, right? I thought we saw that this color is a little bit off then. Should be brown, then orange. No, red, then orange, then green. Reddish brown, how it starts. Okay. And then, of course, the solution changes color due to the oxidation state changing from 6+ in Cr to 3+ on, that should be an arrow, by the way, not R. That should be an arrow. Yeah, a little bit typo here. Okay. And okay, that is all for this one. Now, one thing before we finish class, remember that your paper 3 is canceled, right? For your exams. However, I was told by my other colleague in Singapore that there are some questions from your paper 3 that they dumped on your paper 2 because you have no paper 3. And one of those questions is giving more detail about what the reflux means, this vertical condenser, okay? So I want to highlight a few of them here on the board, so go ahead and copy this down because you won't really see it anywhere else. Okay, so what are the things that they will ask you for the reflux, and then we're done with today for this lecture. First, I usually draw this picture again. Condenser. That just looks so wrong. Heat. Then to do this. This would be a chamber out. Water out. Okay, and then this would be water in. You're condensing, obviously. Then there is another chamber here. Okay. So, kind of. Okay. Now, let's see. This is what they were asking you. The top must be open. Okay. And the reason for that is to prevent pressure buildup. Understand? So don't close that top for the reflux condenser. That's one thing you need to know for the top part. Okay. Okay, so you got the water going in here, coming out at the top, right? So how you understand it, you might have to do this for a normal distillation as well. Water coming in, like lower on the reflux and coming out on the top of the reflux. Is basically to prevent air being trapped inside the outer jacket of the condenser, the outer chamber, I mean. This would cause inefficient cooling. Another thing you need to know, okay? As for the heating, this will be the last point. The heating should be adjusted. So the liquid drips into the flask at a slow, steady rate. And the reactants do not froth back up the condenser, back up into the condenser. Okay, that's it. So if you get a question on paper 2 where they ask you to do, you know, that one we did last time with the alcohols, when you use the reflux A, B, C, D, E, and then like the last part of it, be like, oh, okay. They could ask you like, you know, why would you set up your reflux with an open top at the, and you would say because you want to build pressure, something like that. You give like a 1-point answer, right? Or they say something about like the water, okay? How does the water going in and out of your chamber, okay, help prevent, air being trapped, something like that. That's it. It's not a lot more that they add, but this is stuff that you normally did for paper 3. Paper 3 is all about experimental like techniques and how to, reduce errors in your labs. Yeah, but they sometimes just transfer it over to the paper 2. If your paper 2 is 50% of your grade. Yeah. All right. Are we good so far? This is done. Topic 10 is done. I'm going to stop this video and then we can save it on the Google Drive. You can go back and watch it anytime you want.